Welcome back. This will be our final video for Unit 6. And in this video, I'm going to give you a little bit of an introduction and overview of what complex ion equilibria is. And it's exactly what it sounds like. So they are equilibrium reactions that form complex ions. A complex ion is a charged species with a metal ion surrounded by ligands. An example of that is this right here. This is a complex ion. A ligand is something that donates its lone electron pair to an empty orbital of the metal ion to form a covalent bond. So if you remember back from Chem 1 when you learned how to draw Lewis structures, if I draw the Lewis structure for ammonia, here it is with the lone pair. And so the reason that ammonia is considered to be a ligand in this case is because this extra lone pair right here, it's going to donate it to an empty orbital that the metal has, and in turn, it forms a covalent bond that will then create a charged ion or a charged particle, and that charged particle becomes a complex ion. A ligand can be any Lewis base, and if you don't remember from Chem 1 what a Lewis base is, it's just an electron pair donor, which is what I just explained before what a ligand was. So Lewis acid is an electron pair. These four ions or these four chemicals are probably the most common ligands. They're the only ones that we're going to talk about in this class, but there may be others that you find in other resources. These are just the four most common that you need to know for your test. So the four most common ligands that you need to know for your test are water, ammonia, chloride ion, and then cyanide ion. And they each have an extra or at least one extra lone pair electron that can be donated to a metal or shared with a metal to form a complex ion. The last bit on this slide that you need to know is something called a coordination number. And a coordination number is the number of ligands that are attached to the metal ion. The most common coordination numbers are 2, 4, and 6. And so if you look at these examples on the bottom, the subscripts after each ligand just really tell you what the coordination number is. So for this first one, there are 6 water molecules attached to 1 cobalt, giving you a coordination number of 6. In this example, there are 6 ammonias attached to this nickel to form this complex ion. And so the coordination number for this again is 6. The next example, so this cobalt atom is surrounded by 4 fluorines, making its coordination number 4. And the last one, silver, is surrounded by 2 ammonias, making its coordination number 2. Now, you do not need to know how to name complex ions. Their names are just as complex as the formulas. Don't worry about it. You will never in this class or for the AP exam need to know how to name complex ions. You will simply need to be able to recognize them. You will need to determine what the ligand is. You will need to determine what the coordination number is. And you may need to do a little bit of calculations that I'm going to show you, but those calculations are not anything that you haven't seen before. So here's just a picture of what these complex ions look like. So this one, COCl4 with a 2 minus. So you can see this purple atom in the middle is the cobalt, and it's surrounded by the 4 chloride ions, giving its coordination number of 4. This one is an example of a complex ion made with S2O3. This is not a ligand that was mentioned on the last slide, but it is a ligand. And so you can see here is one of those, S2O3, and here's the other one, and then silver is in the middle forming this complex ion. Its coordination number is 2 because there are 2 of those ligands attached to the silver in the middle. Okay, here's some of the math behind how these complex ions form. And the metal ions are added to the ligands one at a time in separate steps characterized by their own equilibrium constants. And so the next couple slides, I think there's 3, I'm going to go through the calculations behind how these complex ions are formed. And again, it's really more of the same equilibrium math that you've already been exposed to, but I wanted to show you in the context of forming a complex ion. So we're looking at the formation of this complex ion, AgNH3, 2 with a +1 charge. And again, it forms in two separate steps. So first you have your silver ion, just one silver ion, that's going to be surrounded by ammonia, and it's going to form this complex ion. This complex ion will then attach with another ammonia to form the final complex ion that we're looking at. And each one of these steps, as it says in the bullet point above, has its own equilibrium constant. All of those species that are present here, so silver, ammonia, this complex ion, and this complex ion, all exist at equilibrium. So none of them go away. None of them are going to be consumed or anything like that. They all exist at equilibrium. And that's one of the reasons why math that goes along with complex ions are so difficult, because there's just so much going on in these solutions. And it's one of the reasons why it's really not covered at this level. It's covered in upper level chemistry classes. Usually the concentration of the ligand is much larger than the concentration of the metal ion, and because of this, we can use approximations to make our lives a little bit easier and to simplify the problems that we're looking at. So if we assume that both reactions go to completion, you can use the equilibrium constants for each of the two steps, and if you add them together, this is an intermediate, so it's canceled in your final equation. Hopefully you remember this a little bit from kinetics when we did this. We also did it at the beginning of the equilibrium unit. And so you're left with one silver ion. You have these two ammonias that are added together and this final complex ion. Works just like Hess's law. Add the two equations together. The difference between equilibrium and Hess's law is that you multiply your two values of K together. So if I wanted to know the equilibrium constant for this particular equation, I would take the K of the first step and the K of the second step and multiply them together. From here, you can use a bra box that I mentioned a couple videos ago to find the concentrations and the equilibrium constant for this particular equation. You're going to assume that the ligand amount consumed is negligible, meaning we don't care about it. And that goes, this right here, this is one of those approximations or the assumptions that I talked about before. So if we consider a solution prepared by mixing 100 milliliters of a 2 molar ammonia solution with 100 milliliters of a silver nitrate solution, you're going to calculate, or you're being asked to calculate the concentration of silver, concentration of this intermediate complex ion, and the concentration of this complex ion when you're done. One of the reactions that are going to occur is the reaction between ammonia and water, but we're going to ignore this one because that's not what we're interested in. Yes, it happens. Yes, it's significant, but the question that's at hand only is interested in what's happening between the ligand and the silver ion. So we're going to ignore any other reactions that happen. So before any complex ion forms, we need to figure out the initial moles of your silver and the initial moles of the ammonia. And to do that, I'm just going to take the molarity times the volume. This is the first step. So I'm going to plug in this value and this value to the bra box. Remember, in the bra box, we use moles. And so I have your before the reaction. Based on our two numbers here, I can see that silver is the limiting reaction, the limiting reactant. And so in my reaction step of the bra box, I'm going to subtract the number of moles of silver. So that goes to 0. Subtract it from the ammonia, which you get about 0.2. Add it to the amount of the complex ion, the intermediate complex ion. Using this right here, this moles, we can then figure out the concentration of this particular ion by dividing it by your total moles, and you get this. So this answers one of the questions that you're being asked. Then, in order to figure out the concentration of the intermediate complex ion and the concentration of silver, we're going to do we're going to look at the 2 steps from a couple slides ago. So this was our first step that we saw, and this was our second step. The order doesn't matter. We're going to look at those 2 equations separately to figure out concentrations. And so the first thing I would do is to set up your equilibrium expression. It's products over reactants. They're all aqueous solutions, and so we can include them all. Once you have your equilibrium expression set up, if you want to just go ahead and plug in numbers, that's fine. I took this and rearranged it so that I got the ion concentration that we're looking for alone. If you don't want to rearrange it, it's fine. I just did. So once you rearrange it, you get that the concentration of the AgNO3 plus is equal to the concentration of the NH32 plus divided by the K value times the ammonia concentration. And then I just started plugging in numbers. This concentration came from the previous slide. So in the bra box in the last slide, we found that the concentration of the AgNH32 plus was 5 times 10 to the negative 4th right here. And so that's what I plugged in here. Your K2 value we got from what was given to you in a question. And then the concentration of the ammonia I did off to the side here using information that was given in the question. So we know that there was 0.2 moles divided by your total volume, and that's where the 1 came from. Do some multiplication division, and you get the concentration of this intermediate complex ion to be 6.1 times 10 to the negative 8. I'm going to do the exact same calculation with the first step, the silver plus the ammonia. Again, set up my value, set up my equilibrium expression. I rearranged it to get silver by itself. It's not necessary, but I did. And then just plug in the numbers that we get. So that answer to the first came here. This I gave you, the value of K I gave you, and then NH3, it's the same as what I did up here on the right. So it's just 1. Solve for it, and you get your concentration of silver. So those are the 3 concentrations that the question was asking you to do. All right, this last slide just goes through summarizing some of the 2 most important things that the last couple of videos are talking about. And it's looking at strategies for dissolving things that are otherwise insoluble in water. And so the first step that we talked about was looking at adding an acidic solution if you have an anion that has a good or effective base with it. And so if you remember from a couple slides ago or a couple videos ago, the effective bases that I mentioned were hydroxide, sulfur, carbonate, oxalate, and chromate. So all of those I mentioned to be effective bases, meaning they are the anion of a weak acid. And so if you have any solid that has those anions, if you add it to an acid, their solubility will be increased. The second way, let me go back a slide. The second way to dissolve an otherwise insoluble solid is specifically looking at solids that have anions that are not good bases. So if it's a good base, dissolve it in water. If the anion is not a good base, so it's an anion that would form a strong acid, it can be dissolved by combining it with a ligand to form a complex ion, and it will then dissolve. So an example would be this right here. If you have silver chloride would not be, chlorine is not an effective base, and so the way to get that white silver chloride to dissolve is by adding some ammonia to that solution. It then forms this complex ion, which will in turn dissolve, and you can get that solid to dissolve. And that's it for the instructional videos for Unit 6. Here is problem set 14. You will have some time in class to work on it and also to ask questions that you have about this.